Most mariners have experienced the heavy seas caused by storms, and every mariner is familiar with the ship damage caused by them. But it's not just damage that results. Lives are lost too. About 20% of ship losses are caused solely by bad weather, and weather is a contributing factor in a further 15%. Some of these vessels are large and well found. Yet there is no doubt that planned avoidance of adverse weather at the outset of a voyage would reduce these appalling losses. Leaving aside rare submarine earthquakes, heavy seas are caused solely by meteorological conditions. An understanding of meteorology and weather forecasting will enable ship's officers to decide if they're likely to encounter a storm. If so, it may be possible to navigate round it. This will always result in safer passages, and frequently faster passages as well. Meteorology is the study of the Earth's atmosphere. This atmosphere extends into space for about 1,000 kilometers. However, weather variations take place in only the very lowest region, up to a maximum height of 16 kilometers. In this region, called the troposphere, the temperature falls with increased height. As a whole, the Earth's temperature changes very, very slowly. So, on average, the heat gained from the sun during the day is radiated back into space at night. However, the heat is not received evenly all over the globe, and neither is it re-radiated evenly. This leads to temperature differences between large air masses in the atmosphere. The weather is the name we've given to the turmoil resulting from these temperature differences. To see how the global weather pattern emerges, take two equal air masses, one at the equator and one at the pole. More heat is received at the equator, so that air mass will be hotter and occupy a larger volume. The pressure in the upper atmosphere at the equator will then be higher than that at the same height above the surface at the pole. Air will move towards the pole to equalize this pressure difference. This leads to low pressure at the surface at the equator, and comparatively high pressure at the pole, causing surface winds to flow away from the pole. The high-level winds, known as the anti-trades, flowing away from the equator, cool and descend at about 30 degrees latitude, giving high surface pressure, the mid-oceanic highs, and causing further surface winds. However, the Earth rotates as the air flows over the surface. This alters the apparent direction of flow, as seen by an observer on the surface. At about 60 degrees of latitude in both hemispheres, the partially cooled tropical air meets the cold polar air at the polar front. This gives rise to the familiar mid-latitude depressions, as well as causing continual movement of the polar front. So the entire global weather pattern evolves from the unequal heating of the Earth's atmosphere. The winds derived from this idealized pattern fit the observed climate well, giving a good general picture of the prevailing winds. Although climatic patterns are useful in navigation, to really plan their voyages, mariners need more localized and detailed information. It is the job of the weather forecasters to supply this information. To do this, they depend on regular and reliable meteorological observations from ships in the deep sea. A teamwork approach.
Southeasterly 4, bucking northeasterly 6, occasionally gale.
The wind speed and direction are important to weather forecasters and mariners. Both these variables can be judged from the sea state. The direction is at right angles to the line of the waves, and the speed is estimated by the Beaufort scale. This, for example, is force 3. The wave crests begin to break, and there are scattered white horses. An average wind speed of 9 knots. The higher states are not as easy to differentiate. This is a force 9 gale. The foam is blown in dense streaks along the direction of the wind, indicating a wind speed of between 41 and 47 knots. These winds, and their accompanying sea states have an increasingly severe effect on the performance of a vessel. It may be necessary to heave too, wasting both time and fuel. It will always be safer to go round a storm. It seems absurd that ships should be unnecessarily navigated into hazardous weather conditions. Yet, this happens every day. To avoid this, officers need to understand weather, and they need to understand weather forecasting. Armed with this knowledge, they will be able to navigate their ships with the maximum of safety for their shipmates, as well as minimum delay. An observation of crucial importance to weather forecasting is the barometric pressure. Generally, on board ship, precision aneroid barometers are used. After noting the pressure tendency from a barograph, the reading is adjusted until the indicator light flickers. Readings are corrected for air temperature and, if necessary, for height above sea level. This height can differ greatly between loaded and ballast passages. The observations are recorded in the meteorological log. These air pressure readings are used to draw isobars, lines of equal sea level air pressure on synoptic charts. These charts are a basic tool of weather forecasting, as they show the position of the different air masses. They are particularly important in forecasting the variable weather associated with middle latitude depressions. Generally, these depressions begin as wave-like disturbances on the surface of the polar front. The less dense warm air overrides the cold polar air at the warm front. The cold air subsides behind the cold front. As the depression develops, the circulation causes the pressure to fall at the center. The system moves in the general direction of flow of the warm air. This warm air accelerates as it climbs to the top of the troposphere, forming jet streams, winds with speeds of up to 200 knots. These jet streams govern the subsequent movement and development of the depression. Eventually, the cold front catches up with the warm front. This is called an occlusion. Sometimes, secondary depressions develop at the point of occlusion. Ultimately, the depression dissipates. In every case, the fronts are accompanied by heavy clouds and rain. The cloud at the cold front is usually cumuliform, that is, column-like in shape, while that at the warm front is normally stratiform, that is, layered. Depressions over the North Atlantic generally travel in an easterly direction, this being the direction of flow of the warm tropical air which is forming the depression, and as a result, the direction too of the jet stream. Areas of high pressure, sometimes called anticyclones, tend to move much less than depressions. This is particularly true of the mid-oceanic highs. The depressions usually move around the oceanic highs and last about a week, dissipating over northern Europe. Similar systems are found in the South Atlantic and North and South Pacific Oceans. Troughs of low pressure evolve from depressions. Ridges of high pressure evolve from anticyclones. Equilibrium is reached between these air masses at different pressures by the redistribution of mass. In other words, the wind blows. Depressions, where they occur, govern the direction of the wind. In the northern hemisphere, the wind will always blow anti-clockwise round a depression and clockwise round an area of high pressure. In the southern hemisphere, the directions of the wind will be exactly reversed. The wind blows nearly parallel to the isobars, crossing them at a small angle from high to low pressure. The closer the isobars are, the stronger the winds. Wind speeds can generally be read from the chart using a geostrophic wind scale. The energy of the wind is transferred to the sea. As the wind gusts, and the sea is seldom flat, waves with different wavelengths and speeds of travel are formed. These waves travel sometimes thousands of miles to become the swell elsewhere. It has been found that to generate a heavy sea, a strong wind has to blow long enough in the same direction over the ocean. This distance in the same direction is known as the fetch. The fetch, the wind speed and direction, can be found from synoptic charts. This information can be used to work out the expected average wave height, and suitable avoiding action can be taken if necessary. Wave height forecasting using nomograms is straightforward for the deep sea, but it's more difficult for coastal waters, as the shape of the seabed must be taken into consideration. The influence of the land is crucial on coastal weather. For example, in the Gulf in winter, the expected weather, dominated by the trade winds, does not occur. This is because of the high pressure which persists for much of the time over Central Asia. This high pressure extends over the Gulf, leading to fair weather and the high sea temperatures and humidity often found there. In colder climates, fog often occurs in coastal waters. Fog and clouds are both formed by water vapor condensing out of the air. This can only happen when the air has been cooled or when vapor is added to it. Let's look first at the theory of fog and cloud formation. A graph of water vapor concentration in grams per cubic meter is plotted against temperature in degrees centigrade. This shows that the hotter the air becomes, the more water vapor it can support. Let's take a mass of air at, say, 20 degrees centigrade, supporting half the water vapor possible, that is, a relative humidity of 50%, and cool it. Eventually, it becomes saturated. The air can support no more water. The water vapor starts to condense onto microscopic dust or salt particles suspended in the air, forming tiny water droplets. The temperature at which this happens is known as the dew point for that particular air mass. To forecast fog formation, the relative humidity and the sea and air temperatures are needed. One of the standard methods of measuring sea temperature uses a rubber bucket. Simple but effective. It is important to let the bucket fill and empty over a period of time, as it may at first have a very different temperature from the sea. The air temperature and relative humidity are measured with a matched pair of thermometers hung on the windward side of the ship. One thermometer has a dry bulb, the other a bulb surrounded by wet muslin. Evaporation from the muslin lowers the temperature of the wet bulb thermometer by latent heat withdrawal. After 10 minutes, the rubber bucket is raised and the sea temperature is measured. The result is entered with all the other observations in the meteorological log. If fog is forecast, it may be possible to avoid it by standing off, for instance. This means a much less hazardous passage in coastal waters. There are 4 ways that fog is formed. Firstly, radiation fog. This occurs over land at night when the ground loses heat by radiation. The air is cooled to its dew point. The fog, so formed, then drifts out over the sea. Secondly, sea fog. This is formed when warm, damp air is blown over a cold sea and so cooled to its dew point. The other 2 types are less common. Mixing, or frontal fog, occurs where air masses of widely different temperature meet. And sea smoke, which only occurs in higher latitudes when a cold offshore wind blows over a warmer sea. Cloud is formed by air rising and consequently cooling to its dew point. To the mariner, the importance of cloud is to indicate the likely weather, such as the passage of a frontal system. It is important that all the meteorological observations are made in as short a time as possible. Also, that they're transmitted without delay in a suitable form to the nearest station on the global meteorological network. For this particular transmission of observations made in the English Channel, this means the Meteorological Office at Bracknell in Berkshire. The data from over 2,500 ships is received here each day. This information is checked to see that it's consistent with previous observations, before being fed into the huge computer that is the center of the forecasting operation. This computer calculates the movements and changes expected in the air at many different atmospheric levels. To do this, it uses multifunction differential equations representing the dynamic and physical properties of the atmosphere. It takes the largest computer in the world to do the job. For the lowest level, data comes from land stations as well as from ships. For the upper atmosphere, information comes from aircraft and balloons released by weather ships and weather stations. A close watch is kept on the computer calculations. Any inconsistencies or unlikely patterns are altered by experienced forecasters. The computer then adjusts its calculations to accommodate this new data. This man-machine mix gives the best possible analysis of the atmospheric development and movement. The computer prints out the results in many different forms, and this entire process continues 24 hours a day, 365 days a year without a break. Data flows in, the forecasts are recalculated, checked, and printed. It is the job of the senior forecasters to turn the mountain of data at many atmospheric levels into actual weather forecasts. With reference to previous charts, the isobars are constructed. Satellite photographs show where there's cloud, and so are often useful in dealing with the positioning of warm and cold fronts, a crucial factor in middle latitude weather. Not only does the temperature change at a front, it can be seen from the isobars that the wind changes direction. In the northern hemisphere, the wind veers. In the southern hemisphere, it backs after the passage of a front. From these surface-level forecasts, wind and wave forecast charts are computed for the use of those at sea. The Meteorological Office was originally established in the days of sail solely for the benefit of mariners. This tradition is perpetuated in the Gale Warning Service, one of the priority operations of the Central Forecasting Office. In the same tradition is the Ship Routing Service. For not only is meteorological information received at Bracknell, the results of the work here are also transmitted to other weather stations and for all kinds of commercial applications. Also, via facsimile machines to everyone who has the equipment to receive it. These machines transmit an entire map. The information available in this way is staggering. It includes weather forecasts, wave height forecasts, surface wind, surface temperature charts, ice and upper air information, as well as satellite photographs. These photographs have completely revolutionized the locating and tracking of tropical revolving storms. Recognizable by their circular shape and eye at the center, the danger they pose to mariners is well known. These storms are generally 300 to 400 nautical miles in diameter. Their enormous energy is generated by the condensation of water vapor in the ascending air around the inner vortex. The wind spirals inwards from the outer reaches of the storm, releasing torrential rain and increasing in speed. Around the eye, it spirals into the upper atmosphere. A small subsiding air current keeps the eye relatively free from cloud. The eye, an area of intensive low pressure, is usually 25 miles or so in diameter, with low wind speeds. Hurricane-force winds can be expected from the edge of the eye for 50 miles outwards. Although their development is not fully understood, these storms always begin at a latitude greater than 5 degrees north or south, and the sea temperature must be at least 26 degrees centigrade. The area around the eye of a tropical revolving storm represents a threat to shipping second to none in meteorological terms. Yet, the swell generated is smaller than might be expected, because the changing direction and small fetch of the wind gives a confused sea. This kind of sea state information can be deduced, given sufficient time, from synoptic charts. The same information is readily available from the facsimile transmissions in many parts of the ocean. Facsimile machines promise to revolutionize the mariner's appreciation of weather and his ability to avoid adverse and potentially hazardous sea states. For example, a vessel setting out to cross the Atlantic on a great circle route would, under these conditions, run into a storm. The forecast chart shows how the center of the depression is likely to cross the ship's route. The wave forecast chart shows the wave heights in meters that will be generated. Swell heights will add to these, making for extremely heavy seas. A safer route, avoiding the storm, is possible. Such a course might well save a full day on the passage, as well as being more safe. Such technology is only an aid to prudent seamanship. As seamanship assumes a knowledge of and a respect for the weather, facsimile machines are a useful aid to safer ship routing. A knowledge of weather forecasting techniques will enable mariners to make their own interpretations of meteorological information and keep ahead of the weather in their immediate vicinity. Accurate and regular meteorological observations at sea will not only help other mariners, but also those involved in the countless other tasks which depend on regular and accurate forecasting. For mariners, the understanding of meteorology is not just a matter of passing academic interest. It's far more important than that. It is no less than a matter of safety or danger to life. And not only the mariner's own life, but also the lives of all those who will sail with him throughout his career. In bringing a mariner closer to the elements in which he lives and works, there can be no doubt that an understanding of meteorology is fundamental to good seamanship and navigation.